Hey y'all, it's your personal math teacher, Mr. Boyden. I'm back at it again, and today we're going to be starting Chapter 7 of our book, which is going to tell us about sampling distributions. This is the beginning of a section of the course that deals with statistical inference. And the idea behind statistical inference is that if we take a sample and we get our data and we analyze the data, we can try to say that something is true about the population that we're sampling from, but we can't really know that for sure. We will infer information. So for example, right now as I'm recording this video, we are in the COVID pandemic, and so we're teaching from home, and there's been a lot in the news about the trials for the vaccines. So when they do a trial for the vaccine, the population that we're talking about, we want to know if it works and if the vaccine is safe for the entire population of the world, for everybody. But we can't test it on everybody. That'd be kind of a crazy experiment. But we have to get it released sooner than that. So they take a sample of people and run an experiment to see how safe it is. Does that mean that it's guaranteed to be safe for everybody? No, it does not mean that. Now, might it be? It might be, but the fact is we don't know. So what they do is they run a large trial with many thousands of participants. And from those data, they make a distinction and they say, well, we think that it meets our thresholds for safety and for efficacy, and so we are going to do an emergency approval so that people can have this vaccine. Okay, again, so they're inferring that it should be okay, or they're inferring, like, based on the information we have, this is a good thing to do. So let's get into our new learning. The first thing we need to talk about is this question right here. What is the difference between data and a statistic? Okay, data come from a measurement. So data are something that you collect or that you measure. So for example, it could be a test score. It could be the height of individuals. So if I had a list of people's heights, then I would have data about those people's heights. A statistic, it's something that you do with it. It could be a calculation, it could be a single number. So it's a statistic is something that describes a data set in some way. Okay, and let's get some examples of that down here. Examples are things like the mean. Okay, so consider the example over here. If I recorded the heights of all the students in my classroom, and then I found the mean. That would give me an idea. That would say something about where the center or the middle of the heights are for my class. Another measure of central tendency is the median. That's also a statistic. How about the standard deviation? That one measures the spread. Or the range, that also measures spread. Or the IQR. Or the minimum value. Or the maximum value. Or Q1. Or Q3. These are common ones that we see in this class, common statistics. Okay, so that's the difference. This is something that a lot of people, they're very casual in their speech about it. They don't pay attention to if they're saying data or if they're saying statistics, but they are different. Okay, so that's good to know going forward. To understand the concept of a sampling distribution, let's look at an example. And we did this one in class, or I always do something similar to this in class. We'll start with a data set. What I did is I pulled the average scores, or average sample scores from a sample grade book and put them in here. So on the right side, we have the percentages, and then we just have the student number. So I'm going to call this like an index. So, like, oh, student number 11 scored 39% or whatever it is. Okay, so we have an index and a percentage. So what we're going to do now is we are going to use a statistically valid method to take a simple random sample of size 3. And in class, each person recorded 3, and then we put the mean of our sample on a dot plot, which I'll show you in a second. I want to remind you that in your calculator, you would need to go to random integer. And with the I'm using a TI Inspire, so in the TI Inspire, the syntax is you put the range of numbers you want first, so we want numbers from 1 to 22. Then the next number you put says how many you want, so 1, 22, 3. That spits out 3 random numbers from 1 to 22. So what I want to show you now, I want to show you what we came up with in my class the other day. This was the distribution that they got when they ran through this selection method. Okay, and so we had the axis on the bottom, and you can see it's hand drawn. It's just simple and kind of cheap, right? But it goes from 0 to 100, because that's how percentages work, 0 to 100. And then each person put X's or dots for their measurement that they took. Okay, so each of these, this represents a mean of a size 3 sample of an n equals 3 sample. Okay, so remember, mean. This is a whole bunch of statistics on here. These are not data, these are statistics. Okay, although together they kind of start to look like a data set. So from here, I ask my students the question, where is the mean, or what do you think the mean score of that test was, based on what we see here? We did have people that got up in the mid-60s as a highest, and they didn't do anything wrong, by the way. We actually checked their method. They were totally fine. And then we had a few people that were in the low 20s, and we have kind of an aggregation of data right in here. So a lot of people were guessing, 35 to 45, the mean is somewhere in there. And we can kind of see that's the center-ish of this distribution. Let's go see what the actual mean was, because I actually do have it. So if we had had all the data, the actual mean was 39.2. Let's go mark this on that chart. 39.2. The actual mean was about here. Does that look right? Yeah, it looks like it's pretty much the center. Yeah, actually, especially if you consider that's a mean. And this point would kind of skew the mean to the right a little bit from this cluster of data. Yeah, that actually looks spot on. Okay, and that's not a coincidence. Now, what's the point of all this? Because you might be saying like, okay, Mr. Boyden, why would we ever do this if we knew the mean? Totally. Okay, so the reason is because normally when we're doing statistics, we don't know the mean. We don't know. In an election, we don't know how all the people are going to vote until all the people have voted. The best we can do is go take a sample, so take a small portion of them and ask them how they're going to vote, and then try to extrapolate that out to figure out how the whole country or the county or the state, whatever it is, would vote. So in this case, yeah, it's true. Guys, we knew all the data up front, but in the real world, you don't get to. As for another example, consider what I was saying in the beginning of the video about the COVID vaccine. You can't know how everyone is going to react or everyone's body is going to react to the COVID vaccine until you've given it to every single person. And if you were just going to automatically give it to every single person, then there'd be no point having medical trials, because if you're just going to give it to everybody anyway, then why would you even run a trial? We try to run it on a smaller number of people in case the outcomes are disastrous. Because sometimes, especially in medicine, sometimes they are. Or even in a more benign sense, sometimes treatments are not efficacious. Maybe they're not harmful, but if they don't work, it's very expensive to give them out to the whole world. We don't want to spend all this time and money and use our infrastructure distributing a vaccine unless we have a reason to believe that it works. And so we do a trial on a smaller number of people first, and then we distribute it out. That's what we're simulating here. Because yeah, I get it's a small data set of 22, but by taking smaller samples of size 3, we can see that actually, yeah, we can see the distribution. Now, here's the real world problem though. The problem is, what if you are the unlucky soul who does everything right in your study and you end up out here? Your methodology was good, your experimental design is good, your data analysis is you're highly skilled. This can still happen. You can still get these weird samples that are way out kind of on the edge, these outliers. And so there's risk in that. So what we need to learn is how do we mitigate that risk? Okay, in order to answer that question, I want to try to answer this question right here where I'm putting a star right now. What is the smallest possible sample mean that we could have had with this technique, and what was the largest? Okay, the smallest sample mean would have come from if we had happened to have our random number generator generate those last 3 values. Let's figure out what the mean would have been for those. Okay, so I'm just going to add those 3 numbers together and divide by 3. It was possible to find a sample mean of 0.94, which is pretty laughable. So 0.94% on a test average, I don't think so. I don't even know how... that test would have to have a lot of questions and a lot of points. That would be very hard. We would know that was crazy if we got that. But we wouldn't know it was crazy if we got 65% necessarily. What would be the largest? That would be taking these top 3 numbers and finding the average. So I'm going to do that real quick. And the highest we could have had was 86.6. Okay, and that was 86.6%, and that was with a sample size of 3. So, guys, those are really bad results. Imagine if they did something like that on a drug trial, and they had a small sample size, and they just happened to get some weird result that showed that maybe it would show that a really dangerous drug is not dangerous. That would be horrible. Or maybe it shows that a drug that's really good, it doesn't show that it's good. And then we end up throwing away a wonder drug of some kind. So we can't have that. The way we can fix this is if we have a larger sample size. So imagine if our sample size was n equals 5. Then how do these two answers change, the lowest and the highest possible value of the mean? Well, now we would be forced to include all 5 of these values. So what would be the lowest possible mean? I'm going to take a minute to type that in. 4.62 plus 2.78 plus 1.45 plus 1.38, and I'm not going to type in 0 because adding 0 doesn't do anything. Divide by 5, and now all of a sudden, our lowest possible sample is 2.05. So you see how already our worst case scenario is not as far, because remember, we know the true mean is 39.2. So now our worst case scenario for the minimum is not as bad. So to answer this question, how do we expect the variability of our sample mean to change? So a bigger sample leads to less variability. Okay, so in statistics, sample size is king. We want big sample sizes. Now, we've talked in the class before, there's reasons why we can't always do that. Time, money, resources. Potentially, there could be ethical considerations in some cases if we don't know if something is safe or not. There could be ethical issues where we need to find another way that's more ethical, basically. Okay, so big sample sizes are better. If that doesn't feel obvious yet, imagine if our sample size was 22. That would mean that we took all the data. If we did that, we would be guaranteed to find that the mean was 39.2. We would be guaranteed to get it right. And that's a census, right? And so of course it's going to be right. There's no inference then. So big sample sizes are better. The last thing here is, did we capture all the possible samples? What that's referring to is, in class when I did this, was this all of the possible samples that we could have had? Well, no, because we found one down at like 0.9 just now, and we could have had one as high as being up in the, what was it, is it 80s, is that right? 86.6. We could have possibly had one up around 86, so way up here. We just happened to not. Those are unlikely samples, but they are samples that can happen. Okay, so this is not the complete sampling distribution, but this is sort of like an incomplete model of a sampling distribution. Okay, so this is really the concept of, how many times am I going to say it? Sampling distribution is that when we take a sample or run an experiment, we are probably going to get a result that is not the true mean. We're probably not going to get that. In fact, no one in my class got 39.2. Nobody got this exact answer, but we got a lot of answers that were really close to it. We have to understand that that's why we're using inference. We understand that when we run a study, we're not finding the truth for everybody. We're finding that absolute fact, that statistic for our sample, and then we have to think about to what extent can we apply that understanding to the population. We'll do an example of that at the end today. Okay, let's talk about our next thing. We already know what a population is. Normally, or oftentimes, we describe it as thinking about everybody. Like if you talk about the population of the world, that's all the humans, right? Or the population of the United States, all the people in the United States. But it can get way more specific about that. It could be people at our high school who identify as female. That is a population. Okay, so population, I don't want you to think about it as everybody. I want you to think about it as the group that we are trying to make a claim about, or that we are trying to understand better, or trying to find out the truth about. Okay, it's our chosen group that we're studying. Okay, so what we have next here, and I have them in bold, sample statistic and population parameter. People, you are probably never going to see these words paired this way in a book. You're probably not going to see population parameter, and you're probably not going to see sample statistic. I write them out this way because they are alliterative. Sample statistic, they both start with an S, so it's easier to remember how they go together. Population parameter, they both start with a P, so it's easier to remember that they go together. Okay, that's the only reason it's written this way. And the reason I'm doing this is I want you to know that a sample statistic, or a statistic, is a statistic that describes something about the sample. Okay, it's the measurement, or it's the statistic that we record as a result of the data that we collected. And then if it's referring to the population, referring to everybody, then it becomes a parameter. Okay, if it's describing a characteristic of the population. So who would we use? No. When would we use one over the other? What we do is we actually find sample statistics. Sample statistics are to predict or to make a claim. So I'm going to say to infer about the population parameter. This is the name of the game in statistics, is we can get statistics, and from those statistics we try to make a claim or try to have understanding about the parameter. Okay, now this table right here, the purpose of it is so that we can get some of the notation down about these things, because the notation can be confusing. It has the potential to be that way, and so I want to organize it for you here. Because not only do you have to know the symbols, but you have to know which ones go for parameters and which ones go for statistics. So if you need to, please pause the video. Guys, by the way, you can do that at any time. If you want to pause and think and write, always pause the video. That's awesome. Okay, but you may want to pause and draw this table out right now. Okay, so let's get these down. Now, things I want you to know, guys, mean can be both a statistic and a parameter. In fact, I should say it is both. Okay, sample mean, we've seen this before, that's X bar. And the mean of the population symbolically is mu. Okay, so we've seen both of those before. We've never talked until now about why they're different or when to use them. So if you're describing a sample, or if you're describing a statistic from an experiment, that's X bar. And what this means is X bar is a statistic, mu is a parameter. That might not seem like it matters. It's going to matter later though, so you definitely want to learn this one. All right, sample proportion. Sample proportion is P hat, and the true proportion for the population is P. Okay, you could think of it as P hat. Remember, hat, like with inference, it meant that it was a prediction. So P hat, it's like our sample proportion is predicting what it would be, what the proportion would be for the population if we could know. Okay, sample standard deviation, that's S sub x. And then population standard deviation is sigma. So let's do an example down here below. We are going to identify the population, the parameter, the sample, and the statistic in the following setting. A high school student is interested in finding the mean annual tuition for universities in California. So they randomly select 23 universities and found the mean annual tuition to be $19,800. All right, let's write these down. So population, parameter, sample, and statistic. All right, so I think it's probably easiest to start with the sample and the statistic, honestly. That might be easier to think about. So what did they do? They randomly selected 23 universities. So the sample is the 23 universities. Or you know what they did? They took the annual tuition. So let's say the sample is the annual tuition of the 23 universities. All right, so they're collecting data, right? They have a list of 23 tuition values, $23 amounts. Then from that, they make a statistic. What was the statistic they found? They found the mean was 19,800. That's referring to the sample statistic. Remember, both start with an S. So that's the statistic. It's that X bar equals $19,800. I should include the dollar sign. Cash money. All right. Now, the statistic and the parameter are going to be linked. Okay, so if the statistic is a mean, the parameter is also going to be a mean. So it's going to be mu. We're going to describe what that means in just a minute. Because what is the population? In order to understand the population, we need to understand where did they pick the sample from. So how did they pick their sample? A high school student is interested, and we're going to read it again. They want to find the mean annual tuition for universities in California. All right, y'all. Universities in California. That's the only place they're looking. That's the thing they want to know about. Remember that from above? We said the population is the group about which you are trying to make a claim or that you're trying to understand. This person is trying to understand what tuition costs at universities in California. So the population is universities in California. And what that means, since the mean is about, or the parameter is about the population, so the parameter is mu, which is the mean annual tuition of universities in California. Okay, now why is that? Why do we need to write all that out? Why does that matter? Because one of the classic mistakes in statistics that people make, and guys, I don't just mean students, I mean human beings, right? Like I'm talking full-grown adults and people on the news and people who write online, all kinds of stuff. So we want to inoculate you against this kind of false information. If this person only looked at universities in California, then they can specifically only make a claim about universities in California. They can't say like, oh, in the United States, college is so expensive now. Well, this study doesn't say that. This study only can tell you about universities in California. Or someone might say like, well, a study on the West Coast found that. This is not a West Coast study. This is a California study. So we need to be specific, and we need to demand that when people communicate data and statistics to us, that they're specific as well. Okay, because there should be transparency in studies, and this one, granted, is just a kid, so I'm getting kind of serious about it. But there should be transparency. You should be able to find the methodology of the study and the data and all that. Okay, so that's a simple example, but an important one that's going to come up in our next 4 units actually as we go forward. So we'll continue to practice that over and over and over, and eventually it will become easy. All right, next thing we need to talk about is the concept of an unbiased estimator. Okay, so this is not something that is often tested very much, but it's something that does come up and that we should talk about. An unbiased estimator is basically just any statistic that's used to estimate some parameter when the mean of its sampling distribution is the same as the value of the parameter being estimated. That's probably going to make a lot more sense later in this unit. But basically, an unbiased estimator doesn't overshoot or undershoot on what it's trying to do. For example, let's say that we knew for some reason that when you find the mean of your sample, it has a tendency to be higher than the actual mean. Then we wouldn't say that's unbiased. It tends one way or another. That's what bias is, after all. It means that you have a tendency one way or the other. One of the things that people misunderstand about this, so like for example, we consider the mean to be an unbiased estimator of mu. Okay. Some people think, oh, that means it'll always be right. No. It does not mean that it's perfect. Okay, it means that it's not biased in one direction or the other. It doesn't mean that it's always accurate or precise, but in any event. So here's a visual that might make it easier to think about. So some statistics have high variance, like if you had a small sample size, it would have really high variance. And so you can see these dots are kind of all around the bullseye. In this particular case, there's low bias. So you see how in this image right here, not very many of them hit the bullseye, but they're kind of concentrated around the bullseye. It's not like most of them were too high or most of them were too low. Same thing with this one. The points are not mostly too high or too low. They're mostly just right. Versus, look at the examples for high bias. You see how there's like a tendency for them to miss in the wrong direction? So if you were throwing darts and you were either of these people, you would want to make adjustments like, oh, I need to throw a little lower. Versus if you're this person, you just need to become more accurate. You're not throwing too high or too low, you just miss sometimes. Okay, so that's just a reminder on what bias is. Bias is like that it's actually specifically in one direction or another. We'll finish today off with an example. As always, this is a good chance for you to pause the video to try it on your own. Of course, I'm going to be talking through it and explaining it, but this is a good opportunity for you to pause and check your own thinking. Here we go. To determine how much homework time students are going to get in class, Mrs. Lin has a student select a simple random sample of 20 chips from a large bag. The number of red chips in the sample determines the number of minutes in class students get to work on homework. Mrs. Lin claims that there are 200 chips in the bag and that 100 of them, okay, so guys, half of them are red. When Jenna selected a random sample of 20 chips without looking, she got 7 red chips. Does this provide convincing evidence that less than half the chips in the bag are red? That's what we're going to be answering by the end of this question. So maybe I could imagine a classroom where a student pulls up, they go, hey, wait a minute, well, I should have had, 9 or 10 or 11 chips. Why am I getting 7 chips if half of them are truly red? So that's what we're going to answer is this evidence strong enough? Okay, let's do some identification and practice first, though. So, population, parameter, sample, and statistic. Sample is always easy. That's the 20 chips Jenna pulled. The statistic, that was p hat. That was that 7 out of 20 were red, which if we type that in and get a decimal, 35%, or the sample proportion was 0.35. The population is all 200 chips in the bag. And the parameter is P, the proportion of red chips in the bag. Okay, so guys, see what we're trying to do here is the information, the calculation that we know is this one. And what we want to know is this good enough evidence to be able to say that this, the actual number in the bag, is less than 50%. Okay, so let's keep going. What is the evidence that less than half the chips in the bag are red? Well, we know that p hat is 0.35, which is less than 1/2. So that's the evidence we have. We have that one sample that we did, and we're saying, hey, wait a minute, that's a little bit low. Let's find out. So in statistics, what we have to decide, because it's not about trying to win an argument, we're looking for the truth. We want to know, yeah, we have evidence, but is this evidence good enough? So we have to consider what this evidence might mean. And there are 2 things that it might mean. So we're going to try to provide 2 explanations for this evidence. So why are we getting a number that's less than 1/2? Well, the first reason is it could be just random chance. I mean, keep in mind that in this bag, if there are 100 red chips, that means there's also 100 chips which are not red. I mean, it would be possible for us to pull out no red chips, if you think about it. So it could just be random chance. We don't know that because we only took one sample. What's another possible explanation? Another explanation could be that less than half the chips are red. Okay, and so this is what we're trying to decide. This is always the battle when we're doing statistics, is we have to decide which of these is more likely, and is one of them a lot more likely than the other. Is it more likely that it's just random chance, or is it more likely, based on our statistic, is it more likely that actually, less than half the chips are red? So let's continue to explore that. Let's go down to the next one. Let's compare this result to a simulation. This is something that we've done before, right? So they did a simulation of choosing 500, because Jenna only did one, of 500 samples of size 20 from that population of 20 chips, where 100 were red and 100, apparently they're blue chips now. The dot plot on the right shows p hat, which is the sample proportion of red chips in each of the samples. There is a dot at 0.8. Explain what this means. That's this dot right there. That means that 80% of the 20 chips, 20 selected chips, were red. That's what that means. And in this case, 80%, I think that would be 16 out of 20. So in the most extreme case on that side, the person did pick, if assuming, this is because it's a simulation, right? So assuming that half the chips are red, it is reasonable that you could possibly have 16 that you pull that are red. So question 5, would it be surprising to get a sample of p hat is 7 over 20 equals 0.35 or smaller? So let's look at that on the chart. 0.35 or smaller. Is it shocking if you take a sample and it lands in this region of the graph? Not really. I mean, be careful how you think about this. You'll be like, well, I mean, it's less than 50%. Of course it is. But that doesn't mean it's shocking, right? I mean, it's not like, oh my gosh, I'm not like totally surprised. Like, I can't believe it. I mean, if I got 20 out of 20, that would be surprising. Or if only one chip was red, that would be surprising. But there's lots of dots here. There's lots of different ways you could get a value that we got, the 0.35, or more extreme. So no, because this happened many times in the simulation. We don't know exactly how many, but plenty of times. So let's answer the final question then. Based on those answers, do we have convincing evidence that less than half of the chips in the large bag are red? Do we have evidence that less than half of the chips in the large bag are red? No, we do not. Okay, because this outcome right here in our simulation, that's something that can happen. Okay, and it's something that happens with some frequency. And so our answer is no. We're going to learn, and we're going to do this more quantitatively. Right now it's kind of like a gut feel. We're going to do this very quantitatively in the upcoming lessons and in the upcoming units. Okay, and really we kind of have explained it up above in all of these. We've already kind of shown why it's, in fact I explained it right here, why that's not good enough. I want to add something to 6 though. I want to make a note. We do not have, so no convincing evidence, but we do have, we do have what we would characterize as weak evidence. Okay, so it's not convincing. Like, I'm not like, oh, definitely, because convincing is like, oh yeah, for a fact, it's definitely not 50-50 in this bag. There's definitely not 100 red chips. So we have some evidence in p hat, in our sample proportion. So it's not like we found. One thing sometimes people want to have like this false binary. We're like, well, we found that it's false, or we found that it's true. No, we didn't really find anything here. Our sample was not good enough for us to be able to say. We were unable to say that there's less than 50% red chips, but we're not saying there are 50% red chips. This evidence up here, this does not suggest that it is. The fact that we got p hat equals 0.35, it doesn't suggest that half the chips are red. It just is not enough evidence to say that it's not. So if we thought about it as like, is our teacher lying to us about this? We don't know. Maybe we have a weak piece of evidence that maybe the manufacturer of the chips is being dishonest. That's a possibility. But we definitely should not be convinced of that off of this little evidence. So guys, that's an introduction to inference in sampling distributions. I think that's going to be enough for today. This has been kind of a long, fun one. I hope this is helpful. Hope you enjoyed it, and I'll see you next time.